Hello everyone. So today we will be discussing about data formats or data representation. So before proceeding with this particular topic, let's recap what we discussed in our previous class. Okay. So in our previous class we discussed what is micro operation, right? We discussed what is micro operation, right? Then we discussed a register transfer language, right? There is a language that is used to represent micro operations, right? Then we discussed types of micro operations, right? And what were those micro operations? First one was data transfer micro operation, right? And within this data transfer micro operation there were three micro operations, which were a register transfer micro operation, bus transfer micro operation, and memory transfer micro operation, right? Then we discussed little bit about arithmetic micro operations. We did not go deep into this micro operation, this part, because we already discussed this in our ALU discussion, right? When we were discussing ALU. Okay. After that, we discussed logical micro operations, right? And finally, we discussed shift micro operations. Okay. So this was our discussion for our previous class. Okay. So let's proceed with our discussion. Okay. So today we will be discussing about data representation. So before going into what data representation is, let's see why we need data representation. Okay. So first of all, as we know, our computer is what? Our computer is basically what? A digital device, right? What do I mean by digital device? It means that it can, it can, it can operate or understand only what? Only binary information or binary data. Okay. And what do you mean by binary data? What is this binary data? Binary data is nothing but sequence of 0 and 1 that has some meaning, that has some meaning, right? Some meaning. That means sequence of sequence of 0 and 1 that represents something, right? That represents something. And now what is this something? What is this something? This something is only two things. What is it? It is either instruction or it is constant variables, etc. We call it data, right? It can be either instruction or it can be data. So why am I telling you this? Like why I came to the conclusion that it can only operate or understand sequence of 0 and 1, that is instruction and data, because we have already discussed in our previous class that CPU is the one that basically does all the operations, right? And the most fundamental or the most primary operation, let's not write it here, the most primary operation of CPU is micro operation, right? Now what is micro operation? If you remember the definition of micro operation was operation performed on what? Operation performed on what? Performed on data inside or information inside what? Information inside registers, right? Now we know that CPU has registers, right? And this register contains data from where? This register contains data of main memory. Whenever we want to put data into a register, we put the data that is already residing into main memory within the process, right? Process of a program, right? So this register will be having either instruction or it will be having data, right? Therefore, micro operation will be performed on either instruction or data, right? Therefore, we can say it can only operate, see, computer can only operate on or understands what? Instruction and data, right? Okay, so I think this is clear. So now what should be our next discussion? So the next discussion should be to know how to define instruction or how to define data, right? How do we represent instruction and data? So we will be seeing format of instruction and format of data, right? How do we represent any instruction or how do we represent any data? Why? Because, so basically, okay, let me take one more page and let me discuss this a little bit. So we already know that, let's suppose this is computer, okay? We provide input to computer and we get some output from the computer, right? This input and this output will be human understandable format, right? Human understandable format, input as well as output, right? And whenever we want our computer to perform certain task, we provide program to our computer, right? And this program will again be written in high level language, like the language that is almost similar to that of English, right? Something like Python, C, Java, etc., right? So we use high level language in order to write these programs. We can't write programs like using 0 and 1. That would be very tedious task, right? So what we do is we write this program in high level language, okay? Now when this program goes inside computer don't know English or high level language, right? It only understands 0 and 1, right? So what happens is there is something called compiler here, compiler, okay? And before running this program, before this computer can execute this program, this this computer has to first compile this program, okay? This computer has to compile this program. Why? Because compiler converts a high level language program to low level language instructions, set of instructions, okay? That means, let's suppose we have two line of code. Let's suppose we have two line of code now, and this two line of code is in high level language, okay? Now this two line of code will be converted into an equivalent set of binary sequences, right? Set of binary sequences. And like this is two line of code, right? And this can be even 500 line of what? Sequence of what? 0 and 1. So I can write line of binary data, right? 500 line of binary data. And now this binary data can either be what? It can either be instruction or it can be data or constants, variables, etc. It can be either instruction or it can be data, okay? So there is another like symbolic representation of each binary sequence. We call it as assembly language, right? we will like represent all these binary sequences using assembly language itself. So whenever I was writing something like this, right, add a I took one example, add r1 comma m of x, right? So we have not this is an instruction, okay, and this instruction will be this instruction will be a part of this entire set of binary sequence, right? But it won't be written like this. So this format is actually assembly language format. There is a totally equivalent or there is one-to-one mapping of assembly language to that of binary sequence, okay? So there are first few uh, first few bits that will be assigned to this add thing, then next few bits will be assigned to the second part r1, then m of x will be represented using the remaining bits of this binary sequence, okay? So there is like a kind of a one-to-one mapping between this is machine code, right? This is machine code, this is binary sequence. There is one-to-one mapping between assembly language and machine code, okay? Therefore 500 line of binary data is also represented using what? Using 500 line of assembly code, okay? 500 line of assembly code, okay? So what compiler will do is a compiler will convert this high level language program into, so sorry, just a second. Yes, okay. So what compiler will do is compiler will convert this high level language program into low level language sequence of set of binary sequence, okay? And this set of binary sequence will again be used to create the process for this program, right? Instruction part will go to this text section, right? And data section, in data section the data will go, right? The global variables and constants, right, they will go to data section, and so on. Like we already discussed, in operating system you have already read about processes, right? So after this, whenever a process is getting generated, this process will have these binary sequences as it is, and they will be present inside main memory, okay? And from main memory, then you already know the entire flow, right? Okay, so what compiler does is compiler converts this high level language to low level language, and what is low level language? Binary sequences. Now these binary sequences must be understood by computer, right? So this compiler will also understand understand what? It will also understand machine code, or the language of what? The language of computer, the language that is defined for computer. You might have remember, you must remember, right? We discussed in our first class that we define a language for computer, right? So it understands this particular language, right? So it understands how we can convert, it understands it understands what all set of instructions are supported by computer, okay? And whenever it converts, compiler converts the program, it converts this program using only this set of instructions, okay? Some combination of this set of instruction, okay? So compiler also understands high level language, okay? So compiler understands machine code or low level language. Compiler understands high level language, and compiler converts high level language to low level language. And this conversion will be dependent on the language that is defined for computer or instruction set. right? I hope I'm making sense here. Okay, so let's see, uh, let's start a discussion of representations or format of our data. Basically, data representation is representation of data, right? And this data is nothing but data that is present inside the high level language program, right? Inside program. Okay, and if you remember, whenever you studied the C programming, right? Whenever you study C programming, you found out that there is something called as primary primary data types, right? Primary data types. All the compound data types were also the part of like a combination of primary data types, right? Structures were also the combination of primary data types. So the most fundamental the most fundamental type of data that is present inside any C programming C program is primary data types, right? And what are those primary data types? It can be integer, it can be floating point, it can be character, right? So we need to represent these things, right? Whenever we are saying data representation, we are basically representing data that is present inside the C program, okay, or any program that we are providing as an input to our computer. Okay, so let's start our discussion. Let me erase it first. Okay. Okay, so basically there are two types of data. Okay, first is number. Okay, number basically can be integer or float, right? It can be either a whole number, it can be an integer, it can be like something that is not having any decimal point and something after that, and we can have a floating point, right, where we have a decimal point and we have something after that as well, right? Okay, so this is a number. One thing that we basically have as a data is number, and the second thing is character, and I'm including the special characters inside this character thing itself. Okay, not just A to Z. Special characters are also the part of this character. Okay, and all the strings that we see, all the strings that we see are basically combination of these characters, right? Combination of characters. So what we need to do is we need to represent number and we need to represent character. Okay, so so in order to represent a character, we basically, like, whenever we are having any variable, string variable, we what we do is we just take each character one by one. Okay, we split this string into multiple characters and each character is assigned some bits. Okay, we assign each character some bits, and we have some representation methodology using which we represent each character individually, and we just do the concatenation of all these characters, and in this way we get the entire string as our binary sequence. Okay, so this is this is what this is this entire thing will be string, right? It can be like for example, if one character one byte is assigned to one character, one byte is used to represent one character, we can use like so this will be one byte, this will be one byte, and so on. Okay, yeah, so this is how we represent a character. And now what are different ways to represent a character, you like represent a character using the bits? So basically there are few well-known representation methodologies. The first one is ASCII. I hope everyone knows what ASCII is, right? ASCII is American Standard Code for Information Interchange. I hope everyone knows it. Okay. There is one more representation, which is extended binary extended binary code decimal for extended binary coded decimal interchange code, EBCDIC. Okay. So these are two representations that we basically use in order to represent a character. Okay, we won't discuss more about these two things. In case it is required, then it will be discussed in your digital logic design. Okay, so as per COA perspective, it is not required. Okay, we will be looking into the number representation. Okay, let's start discussing about the numbers. Okay, so numbers can be represented using two types of representations. Okay, first is fixed point representation. Okay, and second is floating point representation. Okay, floating point representation. And please don't get confused by the name floating here. It does not mean, and fixed here, it does not mean that this is for integer and this is for floating points. No, fixed point can be used to represent integer as well as floating points, and floating point will also be capable of representing integer and floating point. Both of them are just the way to represent any number. Okay, it can either be integer or it can be float. Okay, so let's start our discussion with fixed point representation. Fixed point representation. So fixed point representation basically means that, okay, so let me tell you one thing. Since we are defining, we are trying to represent integer and float, both of these things can be positive and can be negative, right? So again, so fixed point representation can be of two types. It can be signed or it can be unsigned. Okay, now fixed point representation can be signed or unsigned depending on what is the default uh, default thing that we want to assume. So if we assume that the value that is present inside register is always positive. Okay, in that case we use unsigned representation, unsigned fixed point representation, because we don't need the sign, because there is no negative value that we need to represent, right? In that case we use unsigned fixed point representation. But when we want to represent negative values as well, we use signed representation. Okay, signed fixed point representation. And why it is called fixed point representation? Because it has a fixed distribution of bits for integer part and fraction part. Okay, so for example, this is x number of bits, this is y number of bits, and I am talking about, right now I'm talking about unsigned integers. Okay, unsigned fixed point representation, I'm talking about unsigned fixed point representation. Okay, there we have x bits that are assigned for integer part, sorry, integer part. Okay, and y bits that are assigned to fraction part, to represent fraction part. Okay, and the value that is present inside this register will be binary sequence, right? We know that it will be binary sequence. So it will actually be it will actually be decimal to binary converted binary sequence. Okay, it will be decimal to binary converted binary sequence. You all must have already seen like decimal number system and binary number system in digital logic design, right? So we also see the conversions, right, from decimal to binary, binary to decimal, decimal to octal, octal, all those things, right? So the value that will be present inside this register, so this is a register, right? So the value that will be present inside this register will be a binary sequence that is nothing but the conversion of decimal to binary value. Okay, what do I mean by that? For example, if we have 4.5, right, that we want to put inside this register. So first we convert this 4.5 from decimal to binary. Okay, how do we do that? We know that we take point here, okay, and we in order to represent 4, we represent 4 like this, right? And let's suppose this x is equal to 5 and y is equal to 3. Okay, this is 8-bit register. Okay, in that case the remaining bits will be 0, right? And here, since this is 0.5, 0.5 into 2 is 1. Now 1 does not have any fractional part, therefore 1 here, and the remaining bits are 0 0. Okay, so this is how we will be representing 4.5. Now 4.5, when it goes to register, it goes to register as 0 0 1 0 0 1 0 0. Okay, and this representation is also like now registers are already assigned a certain type of representation. Okay, because CPU can't do representation, can't change representation on the go, because like CPU won't be able to understand what is inside register if it does not know how each bit of register is being used, right? Therefore these representations are predefined by the designer. Okay, so so CPU designer will define that each register will represent the value that is present inside each register will be a fixed point representation, will be the value that has been represented using fixed point representation. Therefore 4.5, whenever there is 4.5, it will be converted like this by compiler, and it will be stored here, and CPU will understand that because this is fixed point representation, unsigned fixed point representation, first 5 bits are for integral part, and next three bits are for fraction part, and this is how it will get to know what exact value that is present inside the register. Okay, and it will do the processing accordingly. Okay. So this is unsigned fixed point representation. It will have a fixed like a distribution of bits for representing integer and fraction. Okay, now comes unsigned fixed point signed fixed point representation. Now the second thing is signed fixed point representation. Now we have a sign. Okay, and when we have a sign, what we will do is we will again distribute few bits, distribute our entire register bits into three parts. The first bit will be sign bit. Okay, the first bit will be sign bit. Okay, I think we have already discussed this when we were discussing like sign flag, right? So whenever there is the representation is signed fixed point representation, first bit will be sign bit. Okay, and whenever sign bit is 0, it means the value that is present here is positive, and whenever sign bit is 1, this means that the value that is present here is negative. Okay. So this is sign bit, this is only one bit. Okay, and the remaining x minus 1 n minus 1 bits will be distributed again into integer part and fraction part. Okay, so fixed point representations, when there is a signed fixed point representation, we have we distribute this register bits into three parts, and the first part is of size 1 bit, which is sign bit, and the remaining bits are distributed among integer part and fraction part. So we will discuss three types of signed fixed point representation. So there are three major signed fixed point representation. What are those? Sign magnitude. Okay. Second is one's complement. Okay. And third is two's complement. Two's complement. Okay. So these are three representation, signed fixed point representation, and we will discuss each of them one by one. The only thing that we need to know here is all these three representation will follow this structure. Okay, so what is this structure? First bit is sign bit, and the remaining bits are distributed among integer part and fraction part. Okay, now the only difference between these three will be the value that is present inside integer part and fraction part. Okay, the only difference will be this. Okay, so let's start with sign magnitude. Sign magnitude. Okay, we already know the structure of this representation. First bit is assigned for sign, and few bits x bits are assigned for integer, and y bits are assigned for fraction. Now this part will get populated uh, like uh, as it is. What do I mean by as it is? Okay, let me tell you. So initially what we do is our step one always is to convert from decimal to binary. Okay. Our step one is always to convert from decimal to binary. So what are we converting? We are converting the value that we want to represent, right? Let's suppose we want to represent 4.5 again. Okay, 4.5. Now how can we represent 4.5? If we convert 4.5, we will check for plus sign and minus sign both, but for now just be with me. What we will do is, in step 1 we will convert integer part to binary. We will convert fraction part, which is zero point 0.5, that means to binary, and sorry, to binary. Okay, and then we will put it in integer part and fraction part. Okay, how will we do it? We will based on the padding, we will first put the integer part from, let's suppose this is decimal. Okay, this distribution, the distribution here So this line means the point. Okay, and starting from right to left, we put 0 0 1. Okay, the integer part. And after that, since it is x bits, let's suppose x is equal to 4, y is equal to 3, and this is 1. Okay, so this means that we are representing this value 4.5 for a register of size 8 bit. Okay, so we are trying to represent this value for register. We want to store this value inside register of size 8 bit, and we are representing the value accordingly, and our representation is sign magnitude representation. Okay, so we will start from left right and go towards left 0 0 1, and since x is equal to 4, we will add one padding 0 here. Similarly, in fraction side, we will go from left to right. It will be 1, and remaining 2 bits are 0. These are padding. Okay, let me write paddings as black zeros. Okay, okay, so this is the magnitude part. This is magnitude part. Okay, and we have a sign part as well, right? Sign part as well. And since we are representing, okay, so whenever we are representing plus 4.5, we will have 0, and whenever we are representing minus 4.5, we will have value 1 here. Okay, and this entire value will be stored inside register of size 8 bit. Okay, okay, so let's also look into the range of this value, range of this value, range of this representation. Let's suppose we have 8-bit register, so how many numbers can we represent? Okay, one point. Okay, so I think we won't be needing this, because like we already know that whenever we are representing binary sequence, we can have different combinations, right? And this combination can be, the number of combination can be 2 to the power size of register, which is 2 to the power 8. So in total 2 to the power 8 numbers can be represented, right? And since half of them are positive and half of them are negative, that means our range will become okay, so 2 to the power 7 values will be positive, and 2 to the power 7 values will be negative. Okay, one thing that you need to notice here is, if we are representing 0, in that case we will be having plus 0 and minus 0, right? Because we are because this sign, this particular bit is reserved for sign, right? And I mean 0 does not have any sign, but ideally we need to put something here, right? Either 0 or 1, right? In that case we will be having two representations for 0. This will be minus 0, this will be plus 0. There is nothing like plus 0 and minus 0, but there are two representations for 0. That means out of this 2 to the power 7 plus values, one will be 0, and out of this minus 2 to the power 7 minus values, one will be 0 here, minus 0 here, right? So the range will be from minus 2 to the power 7 minus 1, right? Because 1 is minus 0, right? Minus 2 to the power 7 minus 1 to 2 to the power 7 minus 1. Okay, this will be the range. Again, why is so? Because there were two zeros. Okay, there were two zeros, and this is how this representation is actually defined. We can't do anything about that. Okay, so the only thing which we need to see here is we need to do step one, which is conversion from decimal to binary. And this conversion will directly, this result will okay, so let me okay, sorry. Okay, so this result will be directly considered as the magnitude. Okay, this result will be magnitude part. Okay, result will be magnitude, and it will directly go inside integer part, will go inside integer section, and fraction part will go inside fraction section. Okay, so this is sign magnitude. Let's proceed. Okay, so we also saw the issue with the sign magnitude, right? Because like, so the range should have been one more, right? Because since we have here, actually if we do the summation here, it is 2 into the number of, like, the number of values that we can represent here is actually 2 into 2 to the power 7 minus 1, which is actually 2 to the power 8 minus 2 and plus 1 0, right? Plus 1 0. So the actual number of values that we can represent here is 2 to the power 8 minus 1. So this one space is like not getting utilized. This one space is not getting utilized in sign magnitude. Okay, so this is the issue with sign magnitude. This is not a very major issue, but yeah, this is one such issue. This is one issue that is like present inside sign magnitude way of representing any data, okay, any number. So let's go ahead with one's complement. Okay, let's discuss one's complement. One's complement. So what is one's complement? Again, we already know the structure will be same, right? Sign will be first bit, sign, integer part, fraction part. Again, we will take this 4 bits here, 3 bits here, 1 bit here. Okay, this is 8-bit register. Okay, this part will remain same, 8-bit register. Now let's discuss. Okay, so whenever we are converting any number to a one's complement representation, in that case what we do is we do step one. What is step one? In step one, we convert value from decimal to binary. Okay, now we will get some result out of it, right? We will get some result out of it. Okay, this will be the result. Okay, now we will put a condition here. Okay, if result, no, sorry, we won't put the condition based on the result. We will put the condition based on the number. Okay, based on the number. So how will we put the value inside I and F section? We will put value like this. Suppose this is I and sorry, this is integer section, this is fraction section. Okay, and again, let's suppose we want to represent 4.5 again. Okay, and now this is plus 4.5 for now. Okay, this is 100 and this is 1, right? This is binary representation. Okay, now what we will do is we will follow the same we will check the this sign. Okay, we will check the sign of this decimal. Okay, this value. If the sign is positive, this is exactly the same as sign magnitude. Okay, if the sign is positive, if sign positive, it is same as that of sign magnitude. What do I mean by that? I mean that the value that will go inside this integer and fraction will be 0, 0, 1, and one value 0 padding here. Okay, 0 padding here, and sorry, and 1 will go here. Okay. This will be our integer section, this will be our fraction section, the sign section will have value 0, right? This entire thing will be our value inside register. Okay, now this is about positive values. Okay, let's discuss about negative values. The difference comes when the value is negative. Okay, in that case it is little bit different. Okay, let me, just a second. Sorry. Okay, let's put it here. Okay, let's put this part here. Okay, so what I was saying, I was saying that whenever the sign is positive, we will follow the same representation as that of sign magnitude. The difference comes when the value that is to be represented is negative. If sign negative, okay, in that case we will do the ones complement of the number. What do you mean by ones complement of a number? I will discuss here. Okay, so let's take another page here. Let's suppose now we want to represent minus 4.5. Okay, so again step 1 will be same, right? We will represent it as 100.12, right? Now since the sign here is minus, we will do ones complement. What do I mean by ones complement? First I will do add the padding. First I will add the padding. Okay, 0, 1, 0, 0, 1, 0, 0. Okay, so this will be, this was like this was the value that was supposed to go if the representation was sign magnitude. But since it is ones complement representation, in that case all these bits will get toggled. Okay, all these bits will get toggled, and the bits will go inside, toggled bits will go inside the register. Okay, and that value will represent what? Minus 4.5. Okay? So therefore, sorry, therefore 0 when toggled it will become 1, 1 toggle 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1. Okay, now this value will be our magnitude. Okay, this value will be our magnitude. Okay, this value will be our magnitude. This will be part I, this will be part F, and we will add sign here. Okay, and the sign will be negative, that is 1, right? This value will be representing minus 4.5. Okay, I hope I'm making sense here. So like you can see here, plus 4.5 and minus 4.5 are very like different from each other here. So in like sign magnitude, the in sign magnitude the only difference between minus 4.5 and plus 4.5 was this sign bit, right? But in here in this case, the entire like sequence gets like changed, right? So this is one's complement. Okay, now let's see if the issue persists that we discussed for sign magnitude. Okay, now let's suppose we want to represent 0. Okay, again again the issue is same, right? Because 0 0 0 0, we can't say 0 to be positive or negative, right? But if we see the result of this, okay, so this will represent minus 0. Why? Because minus 1, this one says that this entire part is what? Negative, right? And this is the toggled version. That means actually it was 0 0 0 0 0 0 0, right? It had been toggled, right? And then it has been saved. Therefore the value that this sequence represent is minus 0. Similarly, if we write this sequence will represent plus 0. Now again we have the same issue, okay? Same issue. Therefore issue persist. Issue, let me write it here, write it like this: inefficiency 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 persist in one's complement as well, right? One's complement as well, right? Inefficiency persists in one's complement as well. Therefore the range for 8-bit register will again be from minus 2.7 so minus 2 to the power 7 minus 1 to plus 2 to the power 7 minus 1. This will be the range, and total numbers that are that can be represented here is 2 to the power 8 minus 1, right? This one is the inefficiency here, right? We were supposed to, like, we can actually represent to the power 8 numbers, but we are representing to the power 8 minus 1 numbers. Therefore there is inefficiency, right? So in order to resolve that, uh, uh, came 2's complement. Okay, so what do you mean by 2's complement? We will discuss. Let me add one more page here. Okay, so let's discuss 2's complement. What is 2's complement? 2's complement. So in 2's complement, what we did was, what the person who coined 2's complement did was, again it uh, started with step 1. Okay, whenever we are representing any value in 2's complement representation, we will have step 1. What is the step 1? Decimal to binary conversion, right? Decimal sorry, to binary conversion, right? And we will get a result out of it. Now this result will be saved with some changes accordingly, okay? And what are the based on the condition, okay? Now the condition is, if sign is positive, if the value is positive value. Similarly, take like plus 4.5. Let's take the same example, plus 4.5. If you want to represent plus 4.5, we will represent this value again in exactly the same manner as that of sign magnitude, right? I won't write it again, I will just write directly here, okay? 0 for sign, and the remaining part will be 0 1 0 0 and 1 0 0, right? This will represent plus 4.5. Actually this sequence will represent plus 4.5 whether it is sign magnitude, whether it is 1's complement, or whether it is 2's complement. In all these cases, all three cases, positive part will be seen, will look exactly the same. Okay, the only change that comes is in negative, when we try to represent negative value. Okay, if sign is negative, in that case, let's take an example here, minus 4.5. Okay, so what we do is, here are steps. Okay, first we do ones complement. Okay, first we do ones complement. Okay, after doing the first ones complement, this is step 1, as step 1.1. Okay, step 2.1. Okay, so this is step 2.1. After doing ones complement, we will add 1 to result. Okay, and this value will be our magnitude. This value will be our magnitude. Okay, so let's take an example. Okay, let me insert one more slide. Okay, let's take the same example. Okay, same example, 4.5 minus 4.5. It will be 100.1, right? Now we know that this sign is negative, right? And since we are trying to represent it using 2's complement, we will first do 1's complement. How were we doing 1's complement? Initially we were adding the padding. Okay, 1 0 0. Now after adding this padding, we will toggle each bit. Okay, this is 1, this is 0, this is 1, this is 1, this is 0, this is 1, this is 1. Okay, now the additional step, so this is 1's complement, right? This is magnitude part of 1's complement. If we were supposed to represent this value in 1's complement, this was our magnitude, right? Okay, but in 2's complement we will add one more here. Okay, now it would be 1 plus 1 is 2, which is 1 0, 0 goes here, 1 goes here, 1 1 2, again 1 goes here. Now this is 1. Okay, this 1 remains same, 1 remains same, 0 remains same, and 1 remains same. Okay, now this value goes to, where? This value goes to register, right? With 1 included. Okay, 1 included in sign bit. Okay. 1 0 1 1 1 0 0. So this will represent minus 4.5. Okay, now you might have a question, right? Why we are adding 1 here? Why we are adding 1 here? Why we are adding 1 here? So let's understand it with an example. Okay, let's take an example here. Let's take example of a 4-bit register. Okay, that would be easy, right? Now if it is a 4-bit register, in that case 3 bit is for magnitude, right? And 1 is for sign, right? 1 bit is for sign. Now this magnitude can be, will be of two section, will have two sections, right? One is integer, one is fraction. Let's take integer section. Let's assign 2 bits to integer section and 1 bit to fraction section. Okay, in that case, now let's see what all combinations are possible here. Okay, let's see. So first of all, when sign is 0. Okay, so when sign is 0, sign magnitude, when sign is 0, that means the value is positive, right? And if value is positive, that basically means that sign magnitude, 1's complement and 2's complement, in all these representations the value will be same, the value will be represented in a same manner. Okay, What do I mean by that? Okay, so these are 3 bits, right? So what all combination are possible here? 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1, right? And 0 is by default here. Okay, let's suppose 0 is by default here. In that case, what is the value? What is this value? This value will be, what? This value will be plus 0, right? This value will be, so this is fraction part, this is integer part, right? 0 0.5, 0 0.5. Okay, you can check it out, like you can just calculate, you can convert from binary to decimal. I'm writing it directly here. So this is 1.0, right? Plus 1.0 plus 1.5 plus 2.0 plus 2.5 plus 3.0 plus 3.5. So the biggest number in the positive direction that can be represented is plus 3.5 in 4-bit register. Okay, now this is common to all these 3 representations: sign magnitude, 1's complement, 2's complement. Now let's see when sign is 1, that means when the number is negative. Okay, in that case, again the possible combination again will be 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1, right? These are the only combination that are possible in that case as well. One will be by default here, right? But the numbers will change. What do I mean by that? So this will represent something else. What will it represent? So let's take each one of them. So let's take sign magnitude, 1's complement and 2's complement. Okay, now, okay, now this okay, this 0 0 0 will be in sign magnitude. This part is the magnitude, right? That means we can directly put 0 0 0 is 0, right? 0 and 1, we can put sign negative here, right? In similar way, we can put, this is magnitude, so this is 1 and sign negative. 0.5, right? 0.5 minus 0.5, right? Now this will be minus 1.0, this will be minus 1.5, this will be minus 2.0, this will be minus 2.5, this will be minus 3.0 and this will be minus 3.5, right? Okay, so again, like here we can see that the smallest value that we can represent in like negative direction is minus 3.5 if we use sign magnitude, right? And this is like the representation. Okay, each sequence will represent this value. Okay, this corresponding value. Okay. Now let's see 1's complement. What is 1's complement here? 1's complement was the bits gets toggled and that value is the magnitude. Okay, so that means 0 0 0 becomes 1 1 1 and 1 1 1 1 is 7, right? And 7 is a magnitude. In that case, minus I'm so sorry, we are taking fraction part as well, right? So if it is 1 1 1 with this fraction, this last bit is fraction, right? In that case, the value will be minus 3.5, right? Here 1 1 0, right? It will be minus 3.0. This is 1 0 1, it is what? 2.5. Similarly 2.0, so similarly 1 1.5, this is 1.0, this is 0.5 and this is again minus 0. So we can see here that minus 0, okay, let's take another, yes, this is minus 0 and minus 0. These are redundant representations in one's complement as well as sign magnitude representation. So how is 2's complement different? Okay. When we add one number, when we add 1 to one's complement, what exactly happens? Let's see. Okay, so it will be like in 2's complement, what will be the value? Okay, let's start from the end. Okay, let's start from the end. This is 111. Okay, now let's toggle it. It will become 000. We will add one value, right? That means it will be 001, which means it will become 0.5, right? It will become 0.5. Now this is 001. We will add 1. This will become 010, which means it will become again negative 1.0. This will become negative 1.5. This will become negative 2.0. This will become negative 2.5. This will become negative 3.0. This will become negative 3.5, and this remaining part, this representation is for negative 4.0. Okay, so this is the additional number that we represent instead of representing 0. Okay, instead of representing 0, what we did is we just add one number, okay, and we shifted all the representations and we included one value more, which will be like minus 4.0. Okay, in that case, we already discussed, right? The range for this will be minus 3.5 to 3.5. The range for this will be minus 3.5 to 3.5, but the range here will be minus 3.5 to sorry, minus 4 to 3.5. It will be minus 4 to 3.5. Okay, and if we see the value, the number of uh, like the numbers, the count of numbers that we are representing here will be 7 for this, 7 for this, and 8 for this, 2 to the power 3, which is 8, right? So I hope, okay, sorry, I'm sorry. uh, so if we add, this is just for, okay, no, this is not true. It is 15, 15 and 16, because 2 to the power 4, right? Sorry, 2 to the power 4, 2 to the power 4, and 8 are here, 8 are here, right? In these two cases, 8 were there and 7 were there, right? So 15, 15, and this is 16. So that is why 2's complement is like the most popular one, and we basically like use 2's complement to represent whenever we use fixed point representation, we use 2's complement. Okay, this is preferred. So this is all about fixed point representation. So let's move on to floating point representation. Okay, so let's write the heading here. Okay, floating point, sorry, representation. Okay, now tell me one thing. If we have fixed point representation, what is the need of floating point representation? Why do we need floating point representation? So the basic answer is fixed point representation had point, sorry, fixed point representation had one limitation. Okay, what was that limitation? Okay, let's take an example here and then I will tell you. So initially we took an example of 8-bit register, right? 8-bit register. Now you must remember that if we are using 8-bit register, we can represent 2 to the power 8 numbers, right? And 2 to the power 8 is nothing but 256, right? Now tell me one thing, compared to a real line, is this number big? Is this number big compared to real line? This is very small number, right? The range is very small. Range is very small. Range is very small compared to real line. That means that if we are using 8-bit registers, so actually there was one time when we were using 8-bit registers, right? So if we are using 8-bit registers, we can just represent 256 numbers out of this entire real line, right? And this is actually very less numbers. So in order to resolve this, we wanted another representation. We wanted, we wanted representation that had higher range, right? Higher range. So using just 8 bits, we should be able to represent more numbers compared to this 256, right? Because 256 is very less. Right now we are using like 32-bit registers as well. But to the power 32 is like, if we see it how big numbers we generally use in computers, to the power 32 is also not that big number. Okay, so what we can do is we can switch to another representation scheme, which is floating point representation. Okay, and so first of all, floating point representation provides higher range, right? Now the question will come, how high or how big, right? How big is the range compared to that of fixed point representation, right? So we will resolve, like we will get to know about it when we will discuss how this number representation works, how we represent a number using this particular representation scheme. Okay, so let's start. So first of all, again, let me take an example here for you. So tell me one thing, if we want to represent minus 54 billion, okay, how do we represent it? There is one way, like we represent fixed point representation. If we do fix, so this is, again, this is actually, I'm talking about let's not think about binary, let's think about decimal right now. Okay, for example, your friend tells you what is minus 54 billion. So how do you explain the person? You will say minus 54 billion is minus 54 with 9 zeros ahead, right? 9 zeros ahead. This is one representation. You will say this is the number, right? And actually this is fixed point representation. Fixed point representation. Uh, okay, fixed point representation. Okay. Now we are having the entire number here, right? And we are taking how much space in order to represent this? One for minus, one for 5, one for 4, and 9 zeros here, right? 9 zeros here, 2 here, and 1 here. So we are using 12 unit of space, right, in order to represent this number in this way, right? There is another way that we can represent minus 54 billion. How is that? We can just say minus 54 into 10 to the power 9, right? Now this is very concise, right? This is very concise compared to the first approach, right? This is very concise. Okay, and how many unit of space is required? One unit of space is required for 9, one for 4, one for 5, and one for minus, right? So if we want to represent it here, one we can represent using like one for plus minus, one unit of space will be plus for plus and minus, and one unit of space will be required for exponent, right? at least for this situation, right? So 9 here, right? And 54, 54. Two spaces are required for this part, which is called as mantissa. So this is called as mantissa, this is called as exponent. Okay, so how many spaces are required? We require only 1, 2, 3, 4. 4 unit of space, and we are able to represent the same number, right? So which one is better, this or this? Obviously, if you want to like concisely represent the number, this is better, right? This is better. Now this is the basic idea of floating point representation. So this is the basic idea of floating point representation. First we take a number, then we make that number in such a way that we have mantissa and exponent, okay, and we represent it using floating point representation. Okay, let's look more into it. Okay, let me add one slide here. Okay, okay, so let's start our discussion. So what we do is, again we will be having a register here, right? What we will do is, as before, we will distribute the bits inside the register in three sections. Okay, first section will be sign section, right? Sign section, and this will be one bit section, right? Only one bit of information will be stored inside this sign. So one binary cell will be allocated to sign. Okay. Now the entire other, this n minus 1 part will be distributed into two sections. Okay, one will be for mantissa and one will be for exponent. So this will be exponent and this will be mantissa. Okay, let me write the spelling here as well. M is mantissa. Okay, is as you know, exponent. Okay, now one more thing. Tell me one thing, when we were using like decimal number, we were doing this 10 to the power 9, right? But when we want to okay, so one more thing here, this 54, let me show it in the previous slide. So this number minus 54 and 9 zeros ahead will have a decimal point, where it will have decimal point here, right? We are not able to see point 0 here, but actually it is there, right? What we did here is we shifted this decimal point in our second representation. We shifted this decimal point to this place, right? This place, and based on the shifts, we multiplied the number of tens, right? That is how we got 10 to the power 9, right? So in a similar manner, when we use binary representations, in binary representations, we can follow the same approach with the base 2. How? Okay, so let's take 101,001. Okay, and point 1, let's suppose point 1, this is the number. Okay? If we multiply it by 2, what will happen? If we multiply it by 2, the result will be 101,001, right? Now decimal place, like this decimal point shifted towards right, right? By one, right? Because we are just multiplying 2. If we multiply 2 again, what will happen? 10 will come, right? And this is actually there are infinite number of zeros here, right? So if we shift towards 1 towards right, we will get 10 from here, right? And point zeros and so on, right? So if we do multiplication of 2 twice, we will be able to shift this decimal point by 2 spaces, right, towards right. Similarly, when we divide this number by 2, what will happen? When we divide this number by 2, in that case, this number, this decimal point will shift here, right? The new number will be 0.11, right? So we are able to shift this number towards left, right? So when we want to represent this particular number into exponent mantissa, whenever it is like it is in binary form, right? So how do we do that? What we will do is we will take the number 101,001.1, okay, and we do two things. We will multiply by, let's suppose we want to shift this decimal point to here, okay, here. What we will do, we will multiply it by, we will divide it by first, we will, okay, sorry, uh, okay, okay, we will divide it by 2, 2, 2, 2, 2, 5, right? 2 to the power 5, right? We will divide it by 2 to the power 5, and that is how we will get our point here. But since we are dividing 2 to the power 5, dividing this number by 2 to the power 5, we will have to multiply it by 2 to the power 5, right? In that way, what we will get? We will get 1.010011 into 2 to the power 5, right? Okay, I think I'm making sense here. Okay, so for like in this situation, what will be the mantissa? What will be the exponent? Exponent will be 5. Okay, what will be the mantissa? Mantissa actually depends on, okay, so for now let's consider this entire part to be mantissa, but actually there is a trick to it. Okay, we do normalization and then we decide which type of normalization is there, and based on that we select mantissa. Okay, so we'll discuss about it. Okay, so I hope I am clear here. So the representation is like this: one bit is for sine, one bit is for sine, x bit is for exponent, and y bit is for mantissa. Okay, 1 plus x plus y will be the size of or width of register, right? A width of a register. Okay, so there is one more interesting thing. So we have the name floating point, right? Floating point representation. Why is that? Because in order to convert any number to exponent and mantissa, we need to float the decimal towards left, right, accordingly, right? And since we are floating this decimal, we say that this representation is floating point representation. Floating point representation. Okay, so let's continue our discussion by taking the same example as before. That was 4.5, right? Let's take the example of 4.5. So how do we represent this? So first of all, step 1 will always be representing or converting to binary. And we already saw that 4.5 is 10, oh, sorry, let me take another pen. Okay, so this 4.5 was actually 4.5 was actually represented as 100.1, right, base 2. Okay, now what is the step 2? Step 2 is normalization. Okay, normalization means converting or floating the point, right? Floating the point, normalizing, creating mantissa and exponent, right? Normalization. So actually there are two types of normalization. One is implicit normalization, okay, and one is explicit normalization. So what is implicit normalization and what is explicit normalization? So implicit and explicit, both these normalization depends on the most significant one. Okay, most significant one, that means the leftmost one. And here what is the leftmost one? This, right? And whenever we represent this, okay, so whenever we want to represent this using even more like numbers, sorry, even more binary cells, we represent it like adding this padding of 0 0 towards the left. But again, the most significant one will be this only, right? And the normalization or floating of this decimal point, will be towards the most significant one. It can be either towards the left of most significant one, or it can be towards the right of most significant one. Okay, now whenever we have, sorry, whenever we have floating point shifted at at right, sorry, shifted at right of this most significant one, that means this. In that case, we say this normalization is implicit normalization. So we will have, okay, we will see the example here as well. Okay, so first of all, let me write explicit here as well. Okay, so whenever floating point or the point is shifted at left of of this most significant bit for both right of and left of most significant bit one. Okay, so we will see this example here. So if 100.1 is there, so if we do implicit normalization for this, we will get the value 1.001 into 2 to the power how much, 1 2, right? 2 to the power 2. And whenever we are doing explicit normalization, in that case we will shift this point towards the left of most significant one, therefore it will be 0.1001, right? And here multiplication will be from with 2 to the power 3, right? 1 2 3. Okay, here there is one thing that is to be noted here. In implicit normalization, right, in implicit normalization, this value, right, this is integer part, right, this is integer part for, at least for this situation, this is integer part, this is fraction part, right? The integer part in this particular scenario, the integer part, I part, will always be 1, right? Whereas in explicit normalization, right, the integer part will always be 0, because we have shifted this point towards the left of most significant bit, the most significant one. And if there is no one here, no one here, that means only padding of zeros are here, right? And in that case there will always be 0 towards the left of one most significant one, right? Therefore the integer part will be 0 here. Okay, in both these scenarios we have the integers fixed, right? In both these normalizations we have integers fixed. So what we do is we actually take the part after the binary decimal, binary decimal as mantissa. So this part after, part after decimal point, let me write it totally, after normalization, sorry, just a second, let me use eraser here. Okay, after normalization part after decimal point after normalization is mantissa. Okay, is mantissa. So I think now you know what exactly which part is called as mantissa, right? And we already know this part is exponent, right? In both the normalization, implicit normalization and explicit normalization, in both the cases this exponent will be different, right? The exponent will be different, and difference between these two exponents will always be 1, right? Because like we are just going towards most significant bit, and we are just either going towards left or going towards right, and since there is just one bit here, the only difference will be of one bit, right? Therefore the exponent will be, the difference between these two exponents will be 1. Okay, so the step 2 is normalization. We can either do implicit normalization or we can do explicit normalization. But if we are not given, if we are not given which normalization is what exact normalization is being performed, in that case explicit normalization is default. Okay. By default, we consider explicit normalization as the actual normalization. Okay, whenever the type of normalization is not mentioned in the paper, you can just consider explicit normalization as a default normalization. Okay, now this is step 2. I hope it is clear till now. So let's proceed. So before going towards step 3, let me tell you the relevance of step 3. Okay, so till step 2, till step 2 we got what all things? We got sign. Sign is very easy, right? We already know, when we see the number here, we know what is the sign. So for the in this situation, the sign is what? Sign is positive, right? So this number is positive. So we can just put sign there in the sign section. We also got mantissa section. Mantissa section is again sorted, right? The only thing that is remaining is now what? Exponent section, right? So what is the trick here? The trick actually is, let's suppose we were having a number like this 0.00 okay, 00 okay, 0 okay, 0.001001. Okay, this was a number that we wanted to represent. Okay, how do we represent that? Again, let's suppose we are doing step 2. In that case, we will see this most significant, sorry, I am sorry, this is not the most significant bit, this is most significant bit, most significant one. We will go towards most significant one, and either we can go to left or we can go to right. Okay, let's suppose we go towards left. Okay, now we are going here. So what will be the result? It will be 0 point, after normalization we will get 0.1001 into 2 to the power. So we are actually dividing it, right? We are actually dividing it by 2 because we are floating the point towards right, right? That means we are actually dividing by 2 to the power 2, which means we are multiplying by 2 to the power minus 2, right? That means our exponent can be negative as well, right? But what we saw here is we have defined the sign for entire number, but we have not defined the sign for exponent, right? We have not defined the sign for exponent. So what is the trick? How are we going to represent it? So what we do is, okay, let me just make the exponent section here. Okay, let's suppose this is exponent, this is exponent. Okay, and let's take 8-bit register. Okay, so let's suppose this is sign, this is 1 bit, this is mantissa. Okay, and mantissa requires how many bits? Let's suppose 4. Okay, let's suppose 4. Okay, so this is, let's suppose 4, this is mantissa. How many are remaining? 4 plus 1 5, 3 are remaining, right? Since there are 3 bits here, that means we can write 0 0 0 0 0 1 0 1 0. What are different possible values? 8 different possible values, right? So what are those? These are the possible different sequences that we can put inside the exponent part. Okay, now but what we need is we need to represent negative numbers as well, right? So the like the most basic thing that we can do is we can split e into two parts, right? One part will be for positive and one part will be for negative. Okay, so what we do is based on this most significant bit we can distribute it into two, right? These are four values, these are four values. We can consider them to be negative, we can consider them to be positive, right? Okay, and 0 is considered as positive. Okay, so this will be 0. Okay, this will be considered as 0. This is not actually 0, but this will be considered as 0. That means what we can do is whenever we want to represent, so how much negative can we go? So since there are four possible negative values that we can put here, right? That means the most negative value that we can put here is -4, right? So in order to represent -4, we are representing it using 0. If we are representing -3, we are actually representing it using 1, -2 as 2, -1 as 3, now 0 as 4, 1, 2 and 3 as 5, 6 and 7. I hope I'm making sense here. This is 1, this is 2, this is 3. So this section will be for result for negative values. 4, 5, 6 and 7, right? The 7, this is the representation for 7 value, right? 7, right? And this 7 is actually nothing but 3. So now this is little bit complicated, right? How do we convert this value? Okay, this is not e. Let's suppose this is small e. Okay, let's suppose this is small e. Let's suppose this is small e. Okay, so this part is small e. Okay, and this part or this part is actually capital E. Okay, the value that will be present here, right? So we can see here there is one pattern here that is being followed. What is that pattern? The pattern here is that the shift between the actual exponent, that is small e, and this big E is 4, right? -4 plus 4 0, -3 plus 4 is 1, -2 plus 4 is 2, -1 plus 4 3, 0 plus 4 4, 4 4 4, right? You might have seen excess 3, right? So excess 3 is nothing but shifting value to adding 3 to all the values, all the numbers, right? This is something like that. Okay, so okay, let me erase this first. Okay, we will be using this space as well. Okay, so I hope I'm making sense here, right? So if we want to represent any exponent in this section, what we will do is we will add one value, one constant value. Okay, and this constant value is known as what? We call it as bias. Okay, this is bias. So what is the formula? Whenever we want to represent the exponent in this part, this is actually the binary representation of binary representation of small e plus bias, right? I hope I'm making sense here. This is the formula here. Bin is binary representation of this part, okay? Okay. And now, what is this bias? How do we calculate this bias? This is again a question, right? How do we calculate this bias? So you can see here, we are deciding to split this part, this entire section, this entire thing into two, right? This entire space, or yes, this entire space into two, negative and positive, and we are doing it using the most significant bit, right? When the most significant bit is 0, then we consider those number as negative. When there are the most significant bit is 1 here, we consider them to be positive. In that case, what will be the bias? Bias will be the remaining part, okay? The remaining part. Why the remaining part? Why it is 4 here? The 4 is here because it is 2 to the power 2. And why 2 to the power 2? Because generally it is starting like this big E is starting from 0, and there is a shift of 4 numbers, and these 4 numbers are actually represented using these 2 bits, right? These 2 bits, only these 2 bits. Therefore there are 2 to the power 2 numbers that are actually like before this 0, right? That are actually negative. Therefore there is a shift of 2 to the power 2. Therefore bias will always be 2 to the power n minus 1. What do I mean? Since it was 3, 1 was most significant bit, 2 was the remaining part, and using these 2 bits we represented all the negative numbers, right? But if this section is n, let's suppose this section is n, in that case 1 will be most significant bit, and this section will be the entire space for n minus 1 bits. In that case we will have 2 to the power n minus 1 negative numbers before 0, right? But we are representing the most negative number by 0, right? So there is a shift of 2 to the power n minus 1 numbers. Therefore this bias will always be equal to 2 to the power n minus 1, where n equal to sorry, let me where okay, where should I write? Okay, let me write it here only, where n is width of exponent section. N is width of exponent section. Okay, just to not make you confuse, like make the confusion, let me erase it. Okay, I hope I'm making sense here. Okay, how are we calculating bias? We are calculating bias using the width of exponent. Width of exponent, if it is n, the 2 to the power n minus 1 is the bias. Okay, and we add this bias to the actual exponent minus 2, right? So we will add this to actual exponent, and this value of, I'm sorry, this value is actually the value that will be put inside this section. Okay, let's write the step here. What will be the step 3? Step 3 will just be to get exponent section, right? This will be add bias to actual exponent, not actual exponent, actual exponent. Okay, bias to actual exponent, and let me write the formula here. E is equal to bias plus small e, where small e is actual exponent, okay, and big E is the biased version of exponent. Okay, we just call it exponent, or we can just call it as a representative exponent. Representative exponent. Okay, this is step 3. Okay, so let's do all these 3 steps. Let's do all these 3 steps to the example that you took. Okay, what was the example? So let's take both the situations. If we are doing implicit normalization, representation using implicit normalization, and representation using explicit normalization. Okay, so let's take it one by one. The value is common, 4.5. Okay, 4.5, right? Now convert into binary. What will it be? 100.1. Okay, and again let's take the register size to be, 8 bit. Okay, 8-bit register. Okay, in that case, what will be the distribution? I'm sorry, the distribution will be, let's decide the distribution as well. Okay, this is the sign bit, the remaining 7-bit, how should we distribute it? Let's distribute it in the similar manner. Okay, okay, let we'll put 4 for mantissa, because there are at least 4 numbers here, right? So let's not make this as an overflow. And so what is overflow, we will discuss. Okay, not an issue. So let's take 4 bits here for mantissa, 3 bits here for exponent, and 1 bit here for sign. Okay, we know the sign, right? Because it is 4.5, the value here will be 0. Let me take another pen. Okay, this is 0. Let me, this is 0. Okay, now let's calculate the mantissa section. Okay, and since we are using implicit normalization, after normalization, after normalization, what will be the value? This will shift towards what? This will shift towards, this is implicit normalization, right? What was happening in implicit normalization? Sorry, in implicit normalization, we are shifting towards the right. We are shifting towards the right of 1. Here we will shift towards the right of 1. It will become 1.001, right, into 2 to the power 2, right? Now this part will go here, right? This will be 0, 0, 1, right? And this 0 will go here. Okay, now the padding will be towards left. Let me write it here. Padding in mantissa is towards right. I'm so sorry, towards right. I'm so sorry, it's towards right. Okay, the padding will be towards right. We will start from the leftmost part, we will write this entire section, and then the padding will be towards right. Okay, okay, so we got sign, we got mantissa. Let's write exponent. Okay, so we have small e equal to 2, right? What will be the bias? Bias will be 2 to the power 3, right? 2 to the power 3 minus 1, 2. 2 to the power 2, which is 4, right? Therefore, I'm so sorry, let me write it here using another pen. Okay, what is the exponent? Exponent is e plus bias, which is again binary representation of e plus bias, which is 4 plus 2, which is 6, right? What is binary representation of 6? It is what? It is 110. So here we will put 110. Okay, now 0, 1, 1, 0, 0, 0, 1, 0, this is the floating point representation of 4.5 when we use implicit normalization. Okay, I hope I am clear here. Okay, let's take explicit normalization. Okay, 0.1. Okay, again the padding is mantissa is towards right in both the cases. Okay, in all the cases. Okay, the only difference is the normalization type, the way the we are doing normalization. Everything else is same. Okay, let's assign bits to this section as well. This is sign 1, 3, 4. Okay, it doesn't look like 3, it doesn't look like 4, but it's okay. So after normalization, let me take the same pen. After normalization, right, what will be the what will happen? This point will go towards the left, right? It will be 0.1001 into 2 to the power 3, right? So this section will go to this mantissa section, right? 1001. Now there is no space, so no padding. Okay, and e here, small e here is 3. Okay, now again bias will be same, right? Bias will be same, the way we calculate bias is same, right? As I told you, the only difference between these two scenarios is the represented normalization. Okay, so the value will be same, e plus bias, and it will be 6, which is 110, right? So the value here will be 110, 110, 110. Okay, and the sign again here is 0. So you can see here, this section remains same, the only difference comes here. Okay, and that difference is also only the shift of this mantissa section towards what, towards right. So this is shifted towards right, this is shifted towards left. Okay, the only difference is one shift, right? I'm sorry, this is shifted towards, this is the reference point, then this is shifted towards left, right? And this is okay, so let it be the reference, and this is shifted towards left. Okay, I hope it is clear till now. So these are the three steps using which step 1, step 2, converting to binary, normalization, and adding bias. These are the three steps that we use to convert any number to its floating point representation. Okay, so till now we have discussed floating point representation and how using just three steps we can represent any number, right? Now let's come to our next question, which is how big is the range, right? This was our initial first question, right? How big is the range and why we are using fixed floating point representation instead of fixed point representation, right? So in order to check how big is the range, let's see the maximum value, maximum positive value that it can represent, maximum negative value it can represent, maximum positive value it can represent. Okay, maximum negative value it can represent, minimum positive value it can represent, minimum positive value it can represent, and minimum negative value it can represent. Okay, let's consider the representation to be sorry, not the representation, the normalization to be for now let's take implicit normalization, which means we will have something like 1 point something something something, right? Okay, so again, so we will use implicit normalization and we will use 32-bit register. Okay, 32-bit register. Let's start with maximum positive. So let's make this 32-bit register. So one bit will be for sign, right? One bit will be for sign. Let's consider the exponent part is of 8 bits, okay, and remaining 23 bits are for mantissa part, okay. Now since we want positive value, right, maximum positive value, that means the value here will be 0, right, and remaining, like in the exponent we want exponent as big as possible, right, so we will put all ones here. Similarly, we want the exact mantissa to be as big as possible, so we'll put 1 1 1 throughout. Okay, so there are 23 ones here, 23 ones here, and 23 and 8 ones here, right? Now let's see the value. Okay, so it will be a positive number as we saw, right? The value will be 1.1111, and this will be what? This will be 23 ones, right? Into 2, into 2 to the power, what? E, exponent, right? To the power exponent. But exponent, actual exponent is small e, but this is biased exponent, right? Biased exponent is representative exponent, right? Big E, okay. So if we want to calculate this small e, okay, so let's calculate it logically. So you must remember that we already discussed in our discussion that this entire section, if we have 8 bits here, this entire section will have 2 to the power 8 numbers, right? And out of these 2 to the power 8 number, 2 to the power 7 numbers are negative, 2 to the power 7 numbers are positives, and inside positive number there is one number which is 0, right? Now if number starts from 0, we know that if total numbers are 2 to the power 7, the biggest number will be 2 to the power 7 minus 1, right? So we can directly write it here, but let me erase it first. So you can directly write here 2 into 2 to the power 7 minus 1, right? Or we can also write it as 2 to the power, okay, let's keep it okay, we can also write it as 127. 2 to the power 7 is 128, minus 1 is 127, so 2 to the power 127. Okay, let's erase this one, okay, and let's continue our discussion. Okay, so okay, let's make this little bit more uh, like let's make it more. So 1.11 we don't know what it is, right? So let's see what it is. So what we can do here is we can shift this floating point to the end, right? In that case we will have 1 1 1 and so on up to 24, 24, because this one is also coming inside, right? 24 ones into 2 to the power, since there are 23 shifts, 2 to the power minus 23 into 2 to the power 127. Okay, now this value will be 2 to the power 24 minus 1, right? 2 to the power 24 minus 1, okay, into 2 to the power 127 minus 23, which is 2 to the power 24 minus 1 into 2 to the power 104. So you can see here the range increased so much, right? Range increased so much. Now this is the maximum positive value that we can represent, right? Now let's see what is the minimum negative number. So minimum negative number is again the same. If you are able to uh, imagine, so minimum negative number is the leftmost negative number that we can represent on any number line, right? So let's suppose this is number line, this is 0, these are positive numbers, these are negative numbers, right? So this is the leftmost negative number that we can represent, right? So in that case the exponent part will be same, right? Because we want to make magnitude as big as possible, right? So this exponent part and mantissa part will be same as that of this situation, right? So it will be 1 1 1 1 up to 1 1 1 1 up to 1, right? Only the difference will be this sign will become 1, right? So in that case, what will be the minimum negative value that we can represent? It will be minus of, we know the magnitude, right? This is the magnitude, minus of 2 to the power 24 minus 1 into 2 to the power 104, right? I hope I'm making sense here. Okay, so we have discussed maximum positive, we have discussed minimum negative, right? So let's discuss these two things as well. Okay, maximum negative and minimum positive. So let's start with minimum positive. Okay, and let me make, sorry, let me draw a line here, let me draw a line here as well. Okay, just for the distinction. Okay, now let's discuss minimum positive. This is positive, therefore the sign bit will be 0, right? It will be 0. Okay, now what is the exponent? Okay, exponent again is 8 bits, right? Exponent is 8 bits and mantissa part is 23 bit, right? So what will be the mantissa and what will be the exponent? Tell me. So in this case, in this particular scenario, we want the smallest value, right? So what we can do is we can make 0 0 0 and so on till the end, right? We can do that, right? And we can make exponent to be 0 0 0 as well. Okay, now this is big E again, right? So how can we represent this? This is positive. Okay, and now this mantissa part is 0 0 0, right? That means the value here will be 1.000 and so on, right? Which eventually will mean 1, right? Into 2 to the power small e. Now what is small e? Small e will be the negative most value, right? We already discussed negative most value will be minus 128. Even if we try to calculate small e, if we try to calculate small e will be big E minus bias, right? What is the bias here? Since the number of bits are 8, that means bias is 2 to the power 7, right? Which is 120, to the 128, right? And since E here is 0, that means 0 minus 128 is what? Minus 128. That is how it is coming here, right? So the value, minimum positive value that is possible here is 2 to the power minus 128. Okay, so this is the minimum value. Okay, now what is the maximum negative value? Maximum negative value is the value with the smallest value with the smallest magnitude, but with a sign, negative sign, right? That is maximum negative. So rightmost negative number is called as maximum negative number, right? How are we going to represent that? We are putting sign here 1, right? And we try to make magnitude as small as possible. We did this exact same thing for minimum positive as well. We wanted to make this magnitude as small as possible, right? So we took all 0 0 zeros here, right? Now we know the magnitude, right? So we can directly write like like how we wrote here. We can directly write the maximum negative value that can be possible is minus of 2 to the power minus 128. Okay, so now you can see here the maximum negative value is this, minimum positive value is this, minimum negative value is this, maximum positive value is this. So if we put it on a number line, this, and let's suppose this is 0, then the range will be from minus 2 to the power minus 128 to, let's consider this value to be a, okay, this magnitude to be a, okay. So just to make it easy, okay, minus a, okay, and here it will be plus 2 to the power minus 128 to plus a, right. This will be the, this will be the, this and this will be the range, right. Anything that is out of this section is out of range, that is overflow, right. But the one thing that you are seeing here is we are not able to represent zero here, right. Zero is missing, so it is very like problematic, right. There is one representation and we are not able to represent zero. That is very big blunder, right. So this was a problem, this was a problem, okay, this was a problem with initial floating point representations, okay. This was the problem with initial floating point representations. And there is sometimes what we want is we want to represent infinites, okay, or minus infinites, or very small values, minuscule values, but we can't represent these things as well, right. So this is also a problem, right? Yes, this is kind of a problem because sometimes we just wanted to represent infinite and minus infinite and we can't do that, right. There is no representation for these two things. So what we can do is we can like do some like we can define some things like some numbers. So this is the representations, right. We can define some sequences for this, and we can use the remaining sequences in order to represent the numbers here, okay. So this is already done by IEEE 754, okay. So there is one standard, this is a standard, okay, this is a standard, that is being followed in order to represent anything uh, in floating point representation. If we want to use floating point representation scheme, we need to follow this particular standard, okay, IEEE 754 standard, okay. So what exactly is IEEE 754 standard? 754. We will look into it. Okay. What exactly is this? We will look into it in our next class. So in our next class, we will see IEEE 754. Okay. Then we will start discussing instructions. Okay. Instructions, type of instructions, and everything about instructions. Okay. So that's all for today's lecture. Okay. Thank you.